This is a Commodore 128 fresh out of surgery for broken 80-column video output. Today on Basic Bytes, I'm going to talk you through how I fixed it while explaining the VDC section of this mainboard and hopefully tell you something useful in the process. Welcome, it's JC, and this is the first appearance of a Commodore 128 on Basic Bytes. This is a Commodore 64-focused channel. However, the 128 will be making guest appearances from time to time. I mean, it does contain a C64 after all. I honestly don't know how popular the Commodore 128 ever was in Canada, and if you have any memories or statistics on that, please leave me a comment. My own memory is that even back when I had my original Commodore 64, and those were plentiful, I never got to use or even see an actual 128 in person. It's not until recent times that I've had the fortune of acquiring two of these machines, and now I'm finally getting the opportunity to play around with them. I was happy to acquire this machine on the understanding that it might not be fully working, and then discover that it was in fact fully working flawlessly with the exception of the 80-column video output in specific. Well, I certainly didn't get a 128 just to use it in 40-column mode or as a C64, but rather to explore its advanced features such as the 80-column video. So, of course, I set about to repair that rather quickly. The chips in question are all underneath this rather substantial metal shield, which not only provides RF shielding to the video circuitry, but also with two prongs on the bottom, some very necessary heat sinking to the two video processors that are on the Commodore 128 mainboard and also happen to be two of the hottest running chips in the system. This is the section of the board that we will be zooming in on as we talk about this repair. So we've tightened up on the metal box, which nicely shields and compartmentalizes the video circuitry on the Commodore 128 mainboard. This half, essentially, is the 40-column video half, which outputs 40-column video to this 8-pin round DIN connector, which is the same as the 8-pin round DIN port on the Commodore 64. This half is the 80-column video half, which outputs 80-column video to this DB9 connector back here. In normal operation, both video chips should always be outputting a signal regardless of whether you are using the 40-column mode or the 80-column mode at any given time. If you start up in 40-column mode, as is the default, the 80-column video chip should nonetheless be outputting a plain black screen to this port. The symptoms I was experiencing is that, for the most part, the 80-column port on this board, as far as I could tell, wasn't outputting anything, as my monitor would just sit there with a bright white wavering flickering screen regardless of whether this machine was on or off. The design of the 40 and 80-column video architectures is very different. The 40-column video architecture borrows directly from the Commodore 64, where you have a main clock crystal, which passes along a clock signal to a timing circuit, which then passes along a clock signal to the VIC-2 chip, which the Commodore 128's VIC-2 chip is a expanded and enhanced version, but nonetheless compatible with the one that is in the Commodore 64. And then from there, the clock signal gets passed on to the microprocessor and the rest of the board. Moreover, this video chip uses main system memory as its video memory, just the same as on the C64. And therefore, if your Commodore 128 won't start up in 40-column mode and you're simply getting a black screen, that could be any one of a number of issues located at a variety of locations across the main board. On the other hand, pretty much everything that drives the 80-column video is contained within these confines, and that is what we are going to be concerning ourselves with in describing its operation and how the repair was executed. In the case of this particular Commodore 128, because I had just received it, the first thing I actually set about doing was replacing all of the electrolytic capacitors on the motherboard. That wasn't specifically to try to fix the 80-column video, but I had resolved to do that in order to change out all of the 35-year-old capacitors, which were more than twice past their expected lifetime, with new ones. And in the event that it turned out to be a bad capacitor, that would also fix the 80-column video as well. It turned out not to be the case, and that was fine. Normally, while recapping a board, you only replace the electrolytic capacitors, meaning these cylindrical ones that look like little canisters that stand up off the board, because those actually have an electrolyte fluid in them which can dry up over time. The ceramic capacitors on the boards, which are these orangish, yellowish, goldish discs, generally do not get replaced because they are solid and, for the most part, tend to work virtually forever unless they sustain damage. Now, during the course of the repair, because it is so hard to maneuver within the confines of this metal shielding, particularly when pulling chips out and such, I did indeed manage to damage and crack a couple of the original ceramic capacitors that were in this area. So, since ceramic capacitors only cost pennies a piece, and I was recapping anyway, what I did was simply replace all of the ceramic capacitors only within this video section of the board, and those are all the little blue dots that you see in here. And again, I figured if it turned out to be a shorted ceramic capacitor, that would have the luck of also fixing the 80-column video, but it wasn't. So while I was doing the recapping that I was going to do anyway, I did the first thing that one does when troubleshooting any sort of a broken circuit, and that is I gave it a close visual inspection on both sides of the board while soldering, and the PCB seemed rather clean. I didn't see any corrosion or any broken traces or anything like that, because clearly if you can see something wrong where there's physical damage, that's more than enough for a video signal not to be getting through, and it didn't seem to be the case here. So then I dived into starting to troubleshoot this 80-column video system, and I tried to come up with a logical order in which to go through these components, which I will describe right now. So this big chip here is the 80-column video chip itself. This is an MOS 8563 revision 9 on this particular board. However, this is simply known as the VDC versus the VIC-2, which is for your 40-column video. Now, obviously what goes through your mind first is that if your VDC is dead, and of course because these do run hot and they're old chips, they are prone to dying, then certainly you're not going to be getting any 80-column video outputted from the machine. Now, thankfully, I have two Commodore 128s, so the first thing I did was try this chip, which is socketed and therefore is very easy to remove. It was actually the only chip in this section that was originally socketed. I took it out and put it in my other Commodore 128, which proceeded to work perfectly. So I therefore knew I had a good VDC and I wasn't going to have to track down another original MOS chip to get this working, but therefore the problem was somewhere else. So here I turn to some diagnostics to try to find out perhaps what else might be wrong, and I have a couple of pet peeves where diagnostics are concerned. One is the fact that people sell Commodore 128s, not in this case, but in general, which are described as working, but only ever show you a working 40-column screen because they have no means of plugging it into an 80-column monitor, and along with that, you can have Commodore's original 128 diagnostic cartridge, which I do, and it will pass every single test with flying colors, even though your 80-column video is completely dead, because the test cartridge runs in 40-column mode and doesn't seem to do anything to specifically probe the 80-column video section for functionality. At the end of the day, it seems like one of the few ways that you can really test whether or not the 80-column video is working is that you must have an 80-column monitor or some device that converts it into a modern display signal in order to see if this is in fact outputting a picture. The DB9 connector at the back here is similar to CGA, but it's not quite. What this actually outputs is RGBI, which is a rather unique signal as far as video signals go, at least nowadays. I did, however, locate some other diagnostic program which was for testing the 80-column video, and although I couldn't get it to fully work, it did seem to go far enough to flash the message to me, bad VDC RAM. Okay, so that gave me my next clue as to what might be going on. In contrast to the 40-column VIC-2, which, as mentioned, uses main system memory as video memory, the VDC has its own VDC RAM, and that is these two chips right down here. Of course, old RAM chips can certainly go bad, and since these are dedicated to the VDC, if those were bad, or if either were bad, that would certainly explain why 80-column video was not going to work even though the rest of the system did. These two chips are 8 kilobytes of RAM each for a total of 16K of VDC RAM on a stock Commodore 128. Unfortunately, the factory default is that these are soldered directly into the main board. So the next thing I did was engage in the rather precarious process of desoldering these ICs while being very careful not to damage any traces on the board. And of course, once you desolder ICs, you never solder new ones into the board, but rather what you do is you solder in sockets into the board so that you can, therefore, forevermore swap new ICs in and out of that slot without ever having to desolder again, and that is precisely what I did. While I am never eager to try to remove ICs that are soldered directly into the main board, I thought I would be quite happy if the problem was in fact the VDC RAM, because while this system has 16K of VDC RAM, later Commodore 128D models actually shipped with 64K of VDC RAM with two 32 kilobyte chips instead of two 8 kilobyte chips, and with sockets in these slots, I would similarly be able to upgrade this Commodore 128 to have the full 64K of VDC RAM, which I understand was also a very common home upgrade back in the day. As you may have guessed by the length of this video, it turned out not to be the VDC RAM, but having put the sockets in, well, at least at that point I knew I could upgrade the RAM if I ever actually got the 80-column video working. At this point, I start reading the Commodore 128 schematics, which are contained within its service manual, which is readily available for download online. What those schematics suggest to me is that a very possible culprit is in fact this logic chip right here. This is not an MOS chip or anything unique. It's simply a standard logic chip which has a bunch of inputs, and based on which inputs are switched on and off, the logic chip decides which outputs should be switched on and off. You can kind of think of it as a traffic controller for the VDC, for the 80-column video system, and what the schematics seem to show is that many of the signals which ultimately reach the video port are in fact routed by that logic chip. My logic was therefore, if we have a working VDC, which I knew, and if we have working VDC RAM, which I also knew because I had already since ordered the upgraded RAM chips to put and try in these slots, and those did not fix the problem, well then, logically, the next problem could very well be the traffic controller. If that's an old chip that has gone bad, and logic chips certainly can go bad, then that would explain why correct signals aren't reaching the video port in the first place. So, I went ahead, I desoldered the logic chip with much care, I resoldered a whole new socket into that slot, I put in a new logic chip, and absolutely nothing changed. There really aren't that many things tied into this system, so at that point I'm thinking, what's left? Which brings me to this bright, shiny crystal right here. The 80-column video system has its own dedicated crystal for its clock frequency. It doesn't derive it from the main crystal, which ultimately gives a heartbeat to the rest of the Commodore 128. At this point, I'm thinking perhaps the reason why I have nothing on the screen is because the monitor can't sync because there is no clock signal, and therefore it has no heartbeat, so to speak, to synchronize to. I replaced the crystal with a new one, and lo and behold, that was the fix that I was looking for. All things considered, since I was recapping anyway, since the lower profile new blue ceramic capacitors will give me better clearance for working in this section in the future anyway, and since the new sockets on the VDC RAM will allow me to upgrade that, really the only, what I will call, wasted effort in this fix was the effort of desoldering and socketing the logic chip, which I think was a logical conclusion that that was the culprit, as I figured there would be a lot more chance of an old IC having burnt out or gone bad than a clock crystal, even though that turned out to be the ultimate culprit. And there you have it, a repaired Commodore 128 with working 80-column video. You've probably also noticed that the ARMSID is making a guest appearance in this video, and although this is certainly not a video about the ARMSID, I would like to take a moment to explain why that's here, because there is a practical connection between its presence and some of the changes that we've just made in the VDCs section of this mainboard. The ARMSID's presence on this board was not a repair, but a decision that I made. Despite that I prefer real SIDs in my Commodore 64s, in my mind, the Commodore 128 was never meant to be a real Commodore 64, but simply a machine that offered Commodore 64 compatibility. And in terms of sound, the ARMSID more than delivers on that description. With that overall mindset, there are two reasons why the ARMSID is a better choice for this board than an actual SID. The first reason is simple heat reduction with hopes for increasing the lifetime of the machine. The original 6000 series SIDs, as would have been found in this model of the Commodore 128, ran quite hot, and by replacing it with an ARMSID which emits no discernible heat, you remove one of the single largest sources of heat from within the confines of the Commodore 128's rather cramped casing. The second reason relates directly to the fact that we now have two socketed VDC RAM chips on this board, which, as mentioned earlier, allows us to easily upgrade the 16K of VDC RAM on this stock Commodore 128 to 64K, as was present on the boards of later Commodore 128D models. Well, the other major practical difference in those later 128D models was that they shipped with an 8000 series SID chip, like the later Commodore 64Cs, rather than the 6000 series SID chip, as was originally in this Commodore 128 and the earlier breadbox 64s. Since the ARMSID can be switched to emulate either the 6000 or 8000 series SID in software, not only do we now have a Commodore 128 that can emulate either the earlier or later Commodore 64s in Commodore 64 mode, but by switching the SID into 8000 series mode, we can also presumably accurately run any software that was specifically written for the later Commodore 128Ds with the 64K of VDC RAM and see and hear it as originally intended by the programmer, thus turning the Commodore 128 into an even greater and more functional Swiss Army knife of a machine than it was in the first place. If you found this interesting or entertaining, please like and subscribe to Basic Bytes for more. You can also easily find us at basicbytes.ca. Thank you for watching.